Good afternoon. My name is Adi Raj, and these are my partners Brian Antonese and Luke Skinner. We are continuing a senior design project from previous semesters, the Micro Air Cycle System. This system is proposed as an alternative to traditional cooling systems such as refrigeration or thermoelectrics. The MAX system functions by electrostatically compressing and expanding a set of vanes in order to cool an enclosed volume of air. These vanes can be modeled as capacitive loads. To improve the efficiency of the MAX and to also save energy, our team has been tasked with designing a drive circuit that transfers charge between alternately charging and discharging capacitive loads. Specifically to this end, we also want a design that is flexible in order to be useful in a wide host of applications. For example, variable voltage is desirable in order to be able to deliver charge to various vane geometries, so as to be able to cool things on the size order of automobile engines all the way down to handheld consumer electronics. Moreover, flexible design is also required in terms of variable frequency in order to cool based on the current temperature. So this semester, what we have accomplished is designing a circuit that takes a AC wall input, passes it through a full wave rectifier and a boost converter stage in order to apply, or in order to deliver a high voltage value to the charge recovery stage of our circuit. This charge recovery stage, pictured at the bottom left, then it uses MOSFETs controlled by a PICAX microcontroller in order to charge the one set of vanes. Once this vane has been completely charged, it discharges into the other set of vanes through controlled by the MOSFET switches. Simulation results indicate that at 500 volts, at 1000 hertz, and at a 50% duty cycle, we're obtaining accurate switching of charge between the two vanes. Once one vane has discharged into the other, the high voltage input compensates for any residual required voltage. And from that, we've obtained simulation results of 99.8% charge recovery. By simply changing out components, or such as adding a boost converter stage or changing the inductor in the charge recovery stage, we can alter voltage levels, frequency, the capacitive load requirements, as well as the duty cycle of the switching. And next semester, we'll focus on the actual implementation of this circuit into a PCB, which will then interface with a mechanical system. Throughout this semester, I have focused on the project management. Luke has focused on microcontroller programming, as well as the pulse width modulation controller. And then Brian has focused on parts, selection, and procurement. We've all been pretty heavily involved in the design and simulation. Any questions?
How big an area or volume is this device capable of cooling?
So right now, that was part of the previous semester's jobs. They kind of modeled the mechanical system. The box that they were using was maybe like 4 inches by 4 inches by 4 inches. But as long as the area is enclosed, they can change the geometry of the vanes, and it should be by adding or subtracting vanes. I guess vane stacks will like thousands and thousands. You can cool a larger area, and all that more vanes do is just increase the capacitive load, which we can accommodate with our circuit.
And the intent here is that this is be more efficient when they're cooling than say heat coolers that do the same thing.
Yeah.
It's also more environmentally safe. So instead of using Freon or other coolants, it's simple electrostatic discharge. Trying to electrotrain for the speaker almost.
So what kind of loss levels do you expect to have effectively parallel resistance in your capacitive load?
I'm sorry,
So I how